Okay, this is the lesson for 12.2 second day. This is a very short lesson. In fact, all these lessons this first week are quite short. So while these are quite simple, nice, gentle introduction to the course, if you're thinking, wow, this Calc 3 is a whole lot easier than I thought it was going to be. Yes, it starts out easy, but trust me, it will get more complicated soon enough. So just enjoy the nice, gentle introduction, and we'll be ready to go. Okay, so today we're going to cover the second day on 12.2, which is our vectors, introduction to vectors. We're going to talk about how to normalize a vector to form a unit vector. And then we're going to talk about the properties of vectors that we can use to evaluate vector expressions. So two real quick topics. Let me switch to the presentation here. Homework tonight is just problems 21, 22, 23. In the in-class sections, we're pretty much going to do the homework in class, but if you do have questions on this, you can talk to me during the before and after tutoring sessions. Okay, so now it should be presenting the screen with the lesson. We're going to pick up where we left off yesterday, and we're going to talk about unit vectors. So a unit vector, simply a vector that has a magnitude of 1. That's all a unit vector means. It has 1 unit of magnitude. Wow, that's pretty bad. Unit vectors have a magnitude of 1. Simple as that. Okay, so let's say we had a vector that was the vector 3, 4. Okay, so if we have the vector 3, 4, that is not a unit vector, right? Because we know that its length is 5. We could compute its magnitude or its length by taking the square root of the sum of the square of the components and get 5. So if we want to convert something to a unit vector to produce a unit vector, so this is a unit vector, then all we need to do is divide all of the components by the length. So you can write that result 3 different ways. You'll have to compute the length, and then you can write it as the vector just divided by 5, or you could write it as being multiplied by 1/5, or you could multiply that scalar in and write it as 3/5, 4/5. Technically, this is the correct definition, right? But you see it written all these different ways. And I'm going to use a word that the book doesn't use, but gets used a lot in engineering, which is normalize. Okay, so I probably shouldn't use this word because the word normal has another meaning, like in statistics and other branches of math. It means a normal curve, a Gaussian distribution. But in the engineering world, they talk about normalizing things, and that just means to bring everything's magnitude to the same magnitude of 1. And so a lot of times I may slip and use this term. If I use the term normalize, what I really mean is make a unit vector out of something. And the way we do that is by dividing by the length. We have to compute the length and divide all components by that length. That's all there is to it. Okay, now everything we've talked about so far, they're extendable, all those ideas, into any number of dimensions. So if we're in 2-dimensional space, then we have x and y components, right, to the vectors. When we do our calculation of length, right, let's say we have the vector 5, 4, right, it has components. Maybe we have 2 vectors. We have the vector 3, 1. We have the vector b, which is 2, 3. If we were to add those 2 vectors together, we would get the vector 5, 4. And then if I wanted to have a unit vector in the direction of the sum of the vectors a and b, then I could take the 5, 4 and divide it by the square root of 5 squared plus 4 squared, which is square root of 41, to get the unit vector in the direction of the sum vector. Right? But all of that could be done in 3-dimensional space if I wanted to, just by adding a z component. Let's say I had vector a was 3, 1, 1, 3 in the x direction, 1 in the y direction, 1 in the z direction to get to this point, right? B would be, let's see, B would be -2 in the x direction, so -2 this way, 3 in the v direction, or y direction, sorry, and then 2 in the z direction, so here. So if you took this, and then you took that same vector, but put it tip to tail with the original, you'd move to here. This would be the sum vector, which happens to be a total of 1 in the x direction, 4 in the y direction and 3 in the z direction. So the sum vector would be 1 comma 4 comma 3 because it has a z component. And then when we compute our length, we would have to use the z squared term in here as well to get the square root of 26. Okay, so everything is extensible into however many variables we want. You could work in R4, R5, R10, R50, but once we get above 3, it starts to become impossible to draw representations. Okay, basis vectors. So when a unit vector happens to be in the direction of the coordinate axes like xy or xyz, then the unit vectors are given the special name basis vectors. And we sometimes assign special symbols to them. So in two-dimensional space, right, the vector that's in the x direction is given the label I. And the one that's in the y direction is given the label j for y. And then if we have a z component, because we're in three dimension, then that's k. So if you see an I, a j, or a k vector, then those are specifically length 1 vectors, and they're in the direction of the coordinate axes. So in 2 dimensions, that means that the I vector would travel 1 in the x direction and none in the y direction, so it'd be 1 comma 0. J would be 0 comma 1, right? In 3-dimensional space, I is 1 in the x direction, 0 for both y and z. J is 0, 1, 0, and k is 0, 0, 1, right? And again, I'm going to show you something that I will try not to do this, but it may slip because of engineering school. So in engineering classes, typically they indicate a unit vector by putting a hat instead of a traditional arrow. For some reason, they use the hat to equal unit vector. So I may do that here and there in the class. Technically, that's not correct for the class because the hat is reserved in mathematics to mean predicted value, like in stats when you have LSR, least squares regression line, y equals a plus bx. For those of you that have taken stats, means predicted y, right? So that's really what hat should mean, but if I slip and use hat, I really mean unit vector, okay? So basis vectors are unit vectors that are aligned with the coordinate system. So other notations, right? If we have a vector and we use our bracket notation 3, 2, and 1, right? You can really say that this is the scalar 3 times the vector I, which is 1, 0, 0, right? Plus the scalar 2 times the vector 0, 1, 0, so that it's all of that 2 is in the y direction, plus the scalar 4 times the vector 0, 0, 1. So since that is the same as this, right? In other words, if you were to multiply this, you would get 3, 0, 0, 0, 2, 0, 0, 0, 4. And then if you added these, you would end up getting 3 plus 0 plus 0, 0 plus 2 plus 0, 0 plus 0 plus 4, and it would be the same. The textbook likes to write vectors in this manner by saying instead of bracket 3, 2, 4, they say 3 times the I vector plus 2 times the j vector plus 4 times the k vector, okay? These are equivalent. However, this is the book method. This is the method we're going to use in the class. I just feel, and Ms. Dastu before felt like this is by far the clearer way to do that. So, but one thing that when we do that is you have to be careful to distinguish between a vector and a point, right? So a vector has angle brackets, right? A point has curved parentheses. All right. All right, and the last thing for today is just talk about properties of vectors. So if A, B, and C are vectors, see here's how the book, they don't put the arrow over it because they put it in bold, but it's just too hard when you draw it. And then the vectors are vectors in Vn, okay, some vector space, and C and D are scalar numbers. So A, B, and C are vectors, but C and D are scalar numbers. Then the following is true. So it's true that if you add vectors, it doesn't matter what order you get the same vector, right? So it doesn't matter the order you add them in. There is a zero vector, by the way. A zero vector is not the number 0. It's a vector that has a 0 for all of its components. So if you have a vector and you add a 0 vector, which means add 0 to all components, you get the same vector. That makes sense, okay? If you have a scalar times the sum of 2 vectors, then you can first distribute the scalar. and take the scalar times each one separately and then add the result, right? So the distributive property works with scalars. And if you have constants, you could decide to multiply one of the constants and then separately multiply them, or you can pre-multiply the constants and multiply, right? If you're adding vectors, you can group them and add these two first and then add this one, or these two first and then add this one, doesn't matter, right? Any vector plus its negative is equal to 0, of course, because they're summing to 0, all the components. And if you have two constants, like let's say you had 2 plus 3 times some vector v, right? It's true that you could take 5 and then multiply the vector by 5, all the components by 5. But if you want to, you could kind of think of it as distributing the v. That is the same as 2, the scalar 2 times v, plus the scalar 3 times v. And then the scalar 1 times a vector replicates itself. So the unit identity, scalar identity. All right, so basically the takeaway from this is, as long as we're only multiplying by numbers, by scalars, then vectors behave the same as numbers, okay? When we get to multiplying a vector by a vector later, we'll have to define that separately. All right, so that's it for today. Homework is in section 12.2, again, in just a few problems. You can get that from the website, and then bring questions to tutoring, or if possible, please join the daily sessions.